Hi everyone, my name is Serdar Salamet, and in this module, I will present you fundamentals of fire engineering. This is meant to be just an overview to establish a sufficient basis to fire engineering concepts before conducting a thermomechanical analysis of the structural models in open seas, which will be in another module. Fire is a load on structures. Similar to earthquake engineering, the structures should be designed to resist the induced internal forces during a fire event. This is the most important point that you will take from this background class video. Here on these pictures, you can see several high-rise building fires. If these buildings were designed against fire conditions or against such typical fires, this kind of damage wouldn't have occurred. Let's get started with the three main pillars or three main branches of fire engineering. These are fire, heat transfer, and structural response, or we can also say thermomechanical analysis of the structures against fire conditions. Fire load and scenarios are essential to estimate the demand on the structure during a fire event. The demand is generally measured as gas temperatures surrounding the structural elements. In order to estimate the gas temperatures, the fundamental principles of fire science and fire dynamics are utilized. As input, the geometry of the compartment in a structure is needed, as well as the amount and type of the fire load. This could be wood, plastic, fabric, or liquid fuels like gasoline. Once the fire or gas temperatures are found, next we get to the heat transfer analysis. Heat transfer analysis basically transforms the gas temperatures in the ambient or during fire event to structural temperatures, and that could be a temperature of the steel member or concrete member or timber member, which is any type of load-bearing member. And once the structural temperatures are obtained, then we can conduct a typical traditional structural engineering analysis. Here, the only difference would be that we're increasing the temperature or temperatures of the structural members in a structural system and observe how it's going to be responding to these fire conditions. Let's start with a real experiment that was conducted in 1960s by NIST, which is National Institute of Standards and Technology. Back then, this setting represented a living room space and furnitures. The fire starts on a couch, and it's quite local, as you can see over here. In the next step, in a couple of minutes, the fire will grow on the couch surface and it will develop soot and hot gas. The hot gas accumulates on the ceiling, as you can see, this black layer. And the fire is, though, still local. So it will create soot, which is, incomplete combustion products. These are hot particulates in the gas, and they form a layer in the ceiling because it's a compartment, there's an enclosed volume. The hot gas and soot layer gets thicker, as you can see here in this picture. The fire is larger now and moves towards the corner wall. So it's still on the couch surface, most of the couch surface now, but it is actually moving towards the corner wall. Right now, this black layer or soot will radiate back a lot of heat to the combustible items or towards the floor where the combustible items are. And this instant is called flashover. Flashover occurs. This is the event when the hot layer gas layer radiates sufficient heat back to the combustible items to increase their temperature to ignition. And a lot of combustible items here where the flames do not touch start to ignite. And you can see this from this coffee table here and some of this frame over here where the fire flames are not in direct contact, but because there's a lot of radiation of heat, the combustible items start to burn all simultaneously. After this, no human survival is possible. This event is the onset of a structurally significant fire. And before that, humans could escape, but now it has become so intense, and the temperatures here would be in the order of 1,000, 1,100 degrees of Celsius. At this moment, these temperatures become quite significant for the structure, and they will change the structural behavior of the system. Let's get to compartment fire dynamics. As combustible items, such as sofa on this picture, burns with a certain mass loss rate, we call it M.F, in an enclosed volume, in this case compartment, it will suck oxygen from the lower layer, in this case M.E, we call it entrained air, and release heat along with water vapor, H2O, and CO2, and some incomplete combustion products such as soot towards the ceiling along the plume. So this gray here represents the plume. So hot gases will rise up due to buoyancy, and they will start to accumulate in the ceiling. And these are, again, hot gases, so they will radiate back to floor and to all the other combustible materials. The hot gases, once they accumulate, they increase the temperature in the compartment, and some of these hot gases are therefore forced out through the openings, through the ventilation openings. Simultaneously, fresh, colder air will flow to the compartment. The flow dynamics are governed by Bernoulli's equation. The equations here of mass balance as well as energy balance in the compartment are solved at each time step to achieve the gas temperature development in the compartment, which is this red letter here. So this T, or the gas temperature, is pretty much what we're trying to solve by using these mass balance and energy balance equations. We're not going to get into details of how they're solved and what all these letters represent, but pretty much these are conservation of law that we need to apply in order to solve the gas temperatures within the compartment. And let's talk about the most important concept of the prescribed fire engineering. Not every compartment fire is, traditionally used in prescriptive fire codes. Standard fire is the most important fire and pretty much the only fire that most of the tabulated values that you can read from fire engineering codes. Standard fire also is called ASTM E119 in the US and ISO 834 in Europe. The plot that you see here is a gas temperature time history in an enclosed environment, aka compartment. Standard fire curve is produced artificially in fire furnaces via controlled burning of cellulosic materials. So this could be wood pellets, for example. But it is actually not a real fire, and there are several reasons for that. First of all, in its initial phase, the temperature rises up to 500 degrees of Celsius within 5 minutes, which is not possible in a building fire unless there's an explosion. Typical building fires will develop, as you have seen in the previous slides, very slowly, within 10 minutes, within 15 minutes, 20 minutes, but not within 5 minutes, the temperature will increase up to 500 degrees. An explosion in this case is out of the scope of this class and module, and it will involve other parameters such as pressure, and we're not going to get into this. In a typical fire, which does not include an explosion, 500 degree within 5 minutes is not possible. Another problem with this fire curve is that it monotonically increases ever and never ceases to stop, which means unlimited amount of fire load. That's also not possible because every compartment, every building will have a limited source of fuel that will burn. Although you ultimately, feed it with oxygen, at some point the combustible mass will deplete, and that basically means that a fire will have some sort of a decay phase where the gas temperatures decrease. And the third reason why this is not a real fire, or standard fire does not represent a real fire, is because there's no ventilation effects. Oxygen input rate is very important for sustained burning and rising gas temperatures. And this equation here is a logarithmic function that represents temperatures of a standard fire with respect to time. And here T is in minutes. Gas temperatures in the building do not directly translate to the temperatures of the structural elements. So we need to conduct the heat transfer analysis. Partial differential equation, PDE, for transient heat transfer, also known as the heat equation, as you can see over here, the second derivative of the temperature, in this case the gradient, is equal to the first derivative of the temperature times a constant, which is a material property. And you can write it down in three spatial coordinates as seen here. And the third equation here is not within the structural element, which, basically the governing mode of heat transfer is conduction, but this one will be governed on the boundary of these elements that basically relates the heat transfer from gas temperatures to the inside the structural element is governed by radiation and convection, as you can see here. For this problem and for the remaining of the module, we really focus on the steel material, and that's the reason we have put thermal properties of steel. But of course, this heat equation is valid for concrete and timber or any other load-bearing member that we decide to do the analysis for. The distribution of temperature within the structural member depends on the temperature-dependent thermal properties, specific heat, and conductivity. Heat is transferred through the structural element's boundary surface via convection and radiation. In this picture, you'll see a fireboard protection. Fireboards are generally made out of gypsum, which is calcium sulfate dihydrate, or with H2O molecule. When when this fireboard is exposed to high temperatures, the water molecules will be released, and they will absorb heat energy, and they will slow down the temperature increase within the steel member. And that's the whole idea, delaying the temperature increase of the structural member by applying fire protection. Spray applied protection serves the same purpose. The spray forms a robust, heat-resistant barrier that prevents the structural steel from reaching critical failure temperatures during a fire. The spray material is generally cement-based or gypsum-based, and this is a common, very cost-effective fire protection type, but it is messy and laborious, as you can see in the picture. Another fire protection material is blanket protection. Fire blankets are often used in fire furnaces for testing and sometimes used in building construction to provide thermal insulation and fire resistance to structures. This type of protection involves wrapping steel beams, columns, or other structural members. The blanket is typically made out of materials like fiberglass or other non-combustible fibers and is designed to adhere closely to the structure via high temperature resistant ceramic nails, as you can see over here. These are ceramic because they do not lose integrity at high temperatures, unlike steel. The last slide on fire protection is intumescent coating. This intumescent fire protection is applied to a surface of steel like a typical coating for corrosion. And upon exposure to high heat or flame, the coating will undergo a chemical reaction that causes it to expand and form a thick insulating char layer, as you can see over here. This layer protects the underlying material from high temperatures. The image on the left is the material before, and the image on the right is the material, the intumescent reaction after the high temperatures are subjected. Intumescent coatings offer a blend of effective fire resistance and aesthetic flexibility, making them a preferred choice in modern building design and construction. In this next slide, you'll see spray applied fire protection material in this construction site. Here, it's a three-story building. The first story of the building is not fire coated yet, so you can see the fire protection is not there, it's bare steel. The second and third floors, you can see the spray applied fire protection. This determining the thickness of this fire protection is essentially one of the most important contributions of a fire engineer during construction phase. It involves not only conventional structural engineering calculations, such as demand capacity estimations for the member, but also compartment fire temperature estimation and heat transfer calculations. Let's jump into the last and the most important aspect of fire engineering, the effect of fire to the behavior of structures. The effect of fire to a structural element or structural system comes in several ways. The steel expands as it heated and contracts as it cools. When the fire is exposed to member cannot expand, the free thermal strain is converted to mechanical strain, and therefore it induces stress in the member. The structural analysis doesn't only involve thermal elongation. It also has other problems or other difficulties that is not present in traditional structural engineering. First of all, the material, whether it's steel, concrete, or timber, it will behave highly nonlinear when it's subjected to high temperatures. Also, within the structural member or cross-section of the member, temperatures will be different. The distribution of the temperatures will be different. That makes the structural member behave as a composite section rather than a homogeneous section. That is, again, a consequence of non-uniform temperature distribution. Another problem arises because of the thermal expansion and nonlinearity. There will be also nonlinearity in geometry. Second order effects, large deflection, will be another consequence of this fire conditions and structural members. Because of this thermal elongation, as I previously said, they will be, depending on the different boundary terrains, they will be induced thermal forces present in these structural members, which are only induced or only created due to fire. Another difference, and which might be beneficial in this case, is using smaller safety factors for structural member calculations in terms of demand and capacity during fire conditions. And the reason for that is, especially for live loads, for example, the codes will assume that during fire, the live loads will be significantly reduced. So this is a beneficial effect, but it's again different when compared to traditional fire structural engineering. Here you see composition of different components of the stress. Here's the mechanical stress, here's the thermal stress, these are the induced stresses, and the stress prime here is the nonlinearity in geometry or geometric nonlinearity. Again, similarly, the strain within a structural member will be composed of mechanical strain and also a combination of thermal strain, free strain, as well as the strain that is due to large deformation theory. The plot here shows the thermal elongation of a typical steel member according to European standards with respect to its temperature. And you can write this, write this curve with these three equations that depends on different ranges of temperature. Another effect of fire on the structural elements occurs due to reduction in stiffness and strength of the steel material when subjected to high temperatures. The plot here shows that stiffness, Young's modulus of steel, let's say 200 gigapascals, starts to decrease rapidly after the steel material reaches 100 degrees of Celsius. So you can see when it reaches to 100 degrees, it starts to decrease rapidly. And the y-axis here is normalized to 1, and it represents the reduction factor. At 500 degrees of Celsius, 40% of the stiffness is already lost, and at 600 degrees of Celsius, 60% of stiffness is lost. Similarly, this plot shows that strength, yielding of steel, let's say 250 megapascals, stays constant until 400 degrees Celsius and starts to decrease rapidly after that. At 500 degrees, 20% of strength is already lost. At 600 degrees, 50% of the strength is lost. So here the strength will start, the strength will start decrease after 400 degrees rather than 100 degrees when compared to stiffness. And lastly, we talk about because of this reduction in stiffness and strength, you can see that the stress-strain relationship of a typical steel will change quite dramatically from ambient temperatures, room temperatures of 20 degrees, all the way to high temperatures such as structural temperatures such as 800 degrees C. Let's say we have a typical steel of 250 megapascals of strength and 200 gigapascals of stiffness. You can see up to 800 degrees, the nonlinearity of steel stress-strain relationship increases. So the steel becomes more and more ductile as well as highly nonlinear as the temperatures increase in the structural member. And the final slide here will attempt to explain the interplay between the demand and capacity of a structural member or structural system. As we already know, as a structural engineer, collapse will occur when the demand exceeds the capacity. And you can see here that the resistance or the capacity is represented by the blue line and demand is represented by the red dotted line. When they cross each other, that's when the structural collapse will occur. And that's also called the critical time. This is occurring pretty much during the heating phase or during when the gas temperatures of the fire will increase. During the cooling phase of fire, when things reverse, the capacity starts to increase as stiffness and strength picks up. The demand decreases due to contraction of steel. Although gravity loads do not change over fire duration, induced forces develop in the members due to thermal elongation and large deflections. And you can see that with the red dotted line as the member heats up because of the restraints in the structural system that's applied to this heated structural member. There will be induced forces and moments in the member that increases demand. But simultaneously, the resistance of that structural member will decrease because of the reduction of the stiffness and strength of that member. So, so this interplay between heating and cooling phase, as well as demand and capacity, will make this, even for one structural member, to make this thermomechanical analysis quite complicated. And here you can see, so when we talk about demand, we're not just talking about the gravity that stays constant, but we're also talking about additional demand that's a function of area and moment of inertia of the cross section, as well as Young's modulus and yield strength of that member material, and of course how the temperatures are distributed within the cross section, and how much of a temperature increase that we get within the cross section, as well as all the boundary conditions that are present. Thank you very much for listening to this module. And in the next module, we will try to attempt to solve an example in open seas using a structural member. Thank you.